Anyways, yeah, so like I was telling you, the way this the USB CLI is set up on this thing is it actually just comes up as a virtual COM port.
Right.
And so you don't need any custom drivers or anything for it. If you look on here, well, actually, yeah, there it is. If you look on here, it actually just shows up as a COM port device with the Microsoft driver. And what's pretty neat is since it's a virtual COM port for the CLI to this buffer board, it's actually compatible with essentially any baud rate. So you can go in here and by default, it works, and that's at, I think, 9600 baud. But you can actually go and crank it all the way up to like 400,000 baud, and it'll have essentially the exact same behavior because the whole CDC stack, the virtual COM port stack actually handles all of that logic.
Oh, nice.
Yeah, it's actually really simple to set up in the code. Got to give ST some credit there. But anyways, so the way that this virtual serial port's set up is it actually exposes the exact same register interface that you can get over the SPI. So if we look, we can open this FX3 application. Like how many different libraries I have associated in this one solution. It takes it like a minute to load.
I mean, on the bright side, if you use the DLLs, you don't have to deal with any of that. So, oh no, that's the thing that happens.
Yeah, I don't know why that host thing is so upset. But anyways, yeah. So the reason it said that the .read write failed is actually because my stall time was too low. So by default, it has a 15 microsecond stall time. And so in order to be able to talk to the IMU, it actually does 2 SPI transactions per read write. So you need a much longer stall time. It's an app which. Oh, I spoke too soon. What is going on in here?
Have you powered it?
Yeah, that's weird. Oh,
it's the wrong FX3.
No, in my infinite genius, I connected to the wrong FX3 board. There we go. That's what I get for having multiple FX3s connected to my computer. There we go.
There we go.
And so now it reset the stall time back to 15 microseconds. So if we set it to 100, that gives it enough time that the FX3 can issue a SPI command to the buffer board, then the buffer can issue 2 SPI commands to the IMU and then retrieve the data. So now if we go and do check that connection, ta-da! And so that actually just did a read write back on the IMU scratch register. So if we go in here, we can actually read the pass-through data from the IMU. So this is the IMU data that's being read through the buffer board. And then we can look at these 3 buffer pages and actually see, like, oh, we've got all these buffer config registers and the write data and read data. But anyways, so what the CLI actually lets us do is we can access these registers through SPI, but the CLI actually lets us access the registers through the same interface, or I guess it's the same register interface, but over USB. And so what I actually did was I set up a few little overloads to make that easier. So you can actually do like read and then the register address. And so right now you can see that we're on page FD, and then I actually support batch reads too. So you can say, oh, I want to read the entire page that we're on. So you can do read 0 to FF, and that actually goes and dumps out the entire register page. And then there's a couple of cool sort of overloads too, where you can do multiple reads. So if you want to say read 0 to 10, and then like 5 times or 6 times, you can actually do that and it'll print them out. And so that's actually pretty useful if you have a register value that's changing, because like, for instance, on the buffer board, there's actually a timer register, a microsecond counter, and that's at, I believe, 4A. And so if you do read 4A, that's the microsecond counter, and so we can read it again, and ta-da, it's counting up. But what's really neat about this is it actually allows you to go and read the IMU registers as well. So right now, if we look at the page register, we're on page FD. But if we actually go and set the page to 0, oh, well, duh.
It's invalid because you only wrote half of it, right?
Yeah, well, I only gave it one argument.
Right,
I just said write address 0. Yeah. So yeah, look at that input validation.
Wow. Fancy.
And so now if we read 0, we're actually on page 0, which is the IMU page. So now we can actually go and read the entire IMU page. And so you can see actually through this USB CLI, you can actually access all the IMU registers. And what's pretty neat with this is it's like the timing is going to be really deterministic, because when you're doing SPI, you have to, like I saw earlier, you have to worry about the stall time and all that. But for this, it's kind of guaranteed that these values won't get printed out until the SPI buffer firmware actually receives the data from the IMU. So it makes it a little bit actually simpler to get set up with. And so you can do the same sort of read overload. So you could say, well, we want to read 0 to hex 10 times, and it'll print out all those values. And so you can see this is actually the, I guess, like the data count register and all that good stuff. And then
I guess the reason that you got zeros there is probably because I think you mentioned that the data rate was really low on this IMU, right?
Yeah, I can actually go here. So if we go in here, we can actually access the same registers, right? And so, well, what's really cool with the CLI is you're actually accessing the exact same registers that you access over SPI. So right now, like I just put the IMU onto page 3. And so if we go in here and we read the page register, we're on page 3 now. And so we can actually go and set the decimate register, which for the IMU to 0, which that'll make our data production rate really high. And so then if we go back and we have to put it back on page 0, but yep, so you can see data counts counting up. And you can actually, so if we look on page 0 for the IMU, what the data count register is, it's address 4. So we can actually just do something like read 4, and then a bunch. And you can actually see these are just all the data count registers coming out. So yeah, that's pretty neat. So that's essentially the read-write functionality for the CLI. It's the exact same as going through the SPI interface. But then there's a couple other sort of quality of life things that are put in there. So if we go back to like this page, if you type in help, it'll actually show you all the commands that I have implemented. But what you can actually do is one of the things that I thought was pretty neat is you can set the delimiter character. So you can actually do delim and then a comma. And then if we do read 010, that's not 0. It actually puts commas in between all the variables. So that's pretty nice because that means if you use a console logger like PuTTY, you can actually just export the log file to a CSV directly. You don't have to do any formatting or anything.
And it's right. And it's a carriage return at the end for your line, like I guess notifying where the end of the line is.
Yeah, so each section of reads is ended with a new line character. So yeah, so that's actually pretty convenient. And so you could just set the delim character to whatever you want. So you could do like plus. Yeah, I don't know if that'd be useful at all, but you can do it. And then what's neat is that actually that value gets placed into this USB config register. So the upper 8 bits of this USB config is the character corresponding to your delimiter. So if you want to set it back to space, you can actually just do this. And then if we go read 010 4, it's now back on space.
That's actually really cool.
Yeah, the register interface is literally identical, which is cool because it makes the functionality identical. Some of the other neat stuff with the USB CLI that's in here is this stream command. And so this is actually sort of how this thing's intended to be used. So you go in here and you do all the configuration that you want to do, write all your control registers and everything, and then you do stream 1. And what that actually is doing is that's enabling a USB data stream operation. And so right now it's not doing anything because there's no data being dequeued. Or there's no data being enqueued, rather. But what will happen is essentially if we go to page 255, which is the data retrieve page, whenever, yeah.
There it is.
It's going really fast actually because of, I think I set decimate to 0, which isn't great, but yeah, so essentially the way the stream works is whenever the data ready watermark interrupt from the buffer gets asserted, it actually goes and dequeues all of the data from the buffer and prints it out to the CLI.
Okay.
And so you can use that. So you kind of have to do a couple of things in parallel. So if we go and set the decimate to something a little more reasonable.
Like one, yeah, whatever you want.
Yeah, so if we set the decimate to something a little more reasonable, just so we're dealing with less data over the CLI, what you can actually do is you can use this, we have this watermark interrupt config register, and that's the number of samples that have to be enqueued into the buffer before a watermark interrupt is generated. So right now it's set to 32, and so that means if we go into this buffer page and start like actually capturing buffered data, every time 32 samples are present in the buffer, it'll actually start printing them out to USB. And so you can actually see, yeah, right now it's actually cranking out all the data that the IMU is spitting out. Or rather it's dequeuing all of the data that the IMU is producing every time 32 samples are accumulated.
And right now it's based off of whatever you have configured in page 254, right? Which is your buffer configuration page, right? So
yeah, so right now it's just sending a bunch of zeros, so it's reading the page register a bunch, which is 3. So not particularly useful. But if we go and do something more useful, like put the data count read request, so that's scaled. So if you put hex 400 in here, it'll actually send a read to the data count register on the IMU. So we can just read the data count a bunch, since that's a nice, like, deterministic number to read. And then we actually have to go put the IMU back on page 0. So yep, back on page 0, we can see our data counts counting up. So now if we go back here, we can actually see this. All these values are actually the data count coming out from the IMU. And then these two over here are actually the timestamp that's associated with the sample. So this is the least significant 16 bits of the timestamp, and then the most significant 16 bits of the timestamp. And so you can see it's actually counting up. And what's pretty neat.
And you implemented the standard timestamp, like Unix timestamp, right?
Yeah, the PPS timestamp. Yeah, I was going to show you that next.
Okay.
So, well, one thing that you can actually do with this thing that's pretty neat is we have this this DIO output configuration register. And so if we look at it right now, we have the data ready for the IMU is set to DIO 1, and then and this essentially nibble right here is this is the watermark interrupt field. And so what we can actually do is, well, actually, so we have the watermark interrupt enabled. So while we're actually doing this data streaming, if we go in the logic analyzer and we look at the watermark interrupt, we should actually see it toggling pretty consistently, right? Because essentially what happens is every time the watermark interrupt gets generated, the USB actually goes and dequeues all the data, and then the watermark interrupt goes away because the interrupt condition is cleared.
Right.
So if you look at this guy, yeah, we can see right here, these are all of these watermark interrupts getting generated, and then brought low, and then high, and then low. So yeah.
Nice.
But anyways,
and that's,
yes, I was.
Well, and to be clear, that's not S clock. That's the watermark. That's the way that you set up the logic analyzer.
it is mislabeled. Yes.
Yeah.
Oh no, actually that might be data ready. Maybe I don't have it plugged. Oh no, it's DIO2 on this board that I have is broken because it was manufactured. That was the first revision of the board. But anyways, we can do a demo. We can actually, so what's cool with the interrupt scheme on this thing is all of them are actually reassignable. So if we go to this DIO output config register and we want to say, instead of having the watermark interrupt be on DIO2, we want to put it on DIO3, we can actually write this register to, 40? And setting it to 40 will actually disable the pin pass-through, so we won't see this data ready signal anymore, and it'll actually put the watermark interrupt on DIO3. So if I go and adjust my logic analyzer to look at DIO3, oops. So we should see now DIO3 on, I think, the CS pin. Yep. And so you can actually see every 300 milliseconds we're getting a watermark interrupt asserted, and then the USB actually comes in and dequeues all the data, and then this right here actually happens when the USB is finished dequeuing all the data. And so in a real application or in a different application where you don't have the stream running, you might actually just monitor this watermark interrupt, and then every time it gets asserted, you can go with the SPI and dequeue all the data the same way this thing's doing. This just does it automatically for you.
Right.
And then you can actually stop the stream too, so we can stop the stream from running. So the buffer is actually still accumulating data. You can see it filling up, but it's no longer being dequeued by the stream.
And you can restart it, I think, just by sending a 1, I think. That's what it was.
You can restart what?
I think you can restart the stream, the USB stream, right?
Yeah. So the way it's set up is you do stream 1 starts the stream, and then stream 0 stops the stream.
Okay.
Yeah. So it's pretty straightforward, and then you can also actually change the stream through this USB config register. So the least significant bit on USB config actually enables or disables the stream. So if we want to enable the stream, you can set that bit, and yep, now we're streaming. And then if you want to disable it, you can just clear it back to 0.
Right.
So essentially that's the meat of the USB functionality. We've got the ability to read, write, dump all the buffer entries sort of on demand, or do this data stream. And so if anyone actually needs more sort of functionality added to the USB CLI, I mean, we can add it pretty easily, or I can add it pretty easily. But I think this is sort of good as a starting point. And like I said before, since it is a virtual COM port, you can actually use it on like a Linux machine, or essentially anything that can open a COM port should be able to talk to this thing. Right.
Yeah, and that makes it extremely versatile, right? Because all of a sudden you can use it in any application. Well, I guess, and because it's a buffer board, using the buffer board and using the buffer functionality, like, you don't really have to worry about data ready. You have your timestamp already. You've got all that stuff, right? So you can recreate whatever you need. You won't lose data.
Yep, that's the thinking. As long as you're able to service it before the buffer gets filled up. And then there was another feature that I actually added based on the feedback we got from the Garage folks. I added this error interrupt that you can set it to generate. And what this is it's actually if any of the diagnostic status register bits are non-zero, or any of the diagnostic status register bits that are covered by this error int config mask are non-zero, it'll actually assert this error interrupt. So you can actually use that to watch and say, oh, did I get a buffer overflow? Did I get like a PPS unlock? Did I get any sort of error condition? And then actually react to that sort of asynchronously. So that's pretty neat. And so this register right here lets you mask out the bits that you don't care about. So for instance, if you just cared about like PPS unlock, you could set it to 40, and then you won't actually get an error interrupt unless, or if any bit besides PPS unlock is set. So it gives you some flexibility there. But anyways, the PPS feature, which I also added based on that feedback, the way that works is you actually can set in this DIO input config, you can pull up the documentation for it, but in the DIO input config, the upper 8 bits allows you to actually configure a PPS input signal. And so that means if you have like a really high stability GPS clock, you can actually use that to reset your microsecond timestamp for the buffer. And the way that's actually set up is we have on page 253, which is the buffer config register page, we have these 4 timestamp registers. So this timestamp register is actually just a microsecond timestamp. So if we read, you can see it counting up. And this one right here is actually the UTC timestamp register. And so the way this thing's intended to be used is you have some higher level system that knows about, I guess, what the current UTC timestamp is. And so you can say it's 1, 2, 3, 4, and then 5, 6, 7, 8. And those registers are actually writable. And you can see right now they aren't incrementing because there's not a PPS signal being applied. But what this UTC timestamp actually lets you do is it lets you provide a sort of known global time. And so the intended use case is you go and you set this register to whatever the current time is, and then you actually configure this DIO input configuration to tell it what the PPS register or the PPS signal is on, I guess.
Yeah, what pin it's on, right?
Yeah, what pin it's on. So if we want to put it on, for instance, like, let's do DIO3 again. So we could do 411. And what that'll actually do is that the 4 says DIO3 is the PPS signal. 0 up here is it triggers on the falling edge. And then the 11 is actually the IMU data ready input configuration. So it's saying the IMU data ready is on DIO1 pos edge triggering. And so then to actually enable this PPS input, what you have to do is you actually send a command. So the idea is you set the current time, and then before the next PPS strobe comes in from your clock source, you actually send this PPS start command. So you send 10, and right now I actually don't have a PPS signal coming in, so actually the status PPS unlock bit gets set. But what we can actually do is if we go into the FX3, we can give it a really crappy PPS signal because it's also just based on a crystal, so it's not going to be super great. But we could just go in here, provide a 1 Hertz PWM input to the DIO3, and we'll actually see that PPS unlock bit cleared out. And now this UTC timestamp register is actually counting up once per second. And what's really cool is every single time this UTC timestamp register counts up, the microsecond timestamp actually resets. And so by using those two sort of in combination with each other, you can actually get the current second, like the UTC second timestamp, and then also the microseconds within that second. Right. So you get a very, very precise but also accurate timestamp. And what's nice is the PPS actually allows us to avoid like having that really heavy clock drift that you get from like a 20 ppm crystal.
Right. Yeah, and then just over time, just as the, if you want to synchronize it, like you said, to a higher order system, now if you want to do vision processing or anything else at a higher level, you can synchronize your inertial data to the exact time that the frame was processed, not, guesstimating about 30 frames per second and anything like that. No, it's exactly what it was, right?
Yeah, it's the exact, and the UTC time is absolute, right? It's any sort of system that you have is going to know what the UTC time is. And so you've got that second accuracy and then microsecond precision within that second. So that's pretty neat. And then the UTC timestamp is actually placed into each buffer entry. So if we look, right now there's 0 just because we had older data that was in there.
You may want to clear the buffer.
Well, the buffer is empty. Why is it? Oh, I unplugged the IMU. That's what it was.
Yep, that'll do it.
Yeah. Well, I was going to show. So something you can actually do that's really cool is the UTC timestamp is actually very accurate for measuring essentially the phase delay between the PPS signal and the IMU data ready. So right now we have this IMU data ready is on DIO1 and the PPS is on DIO3. So what we can actually do is we can enable pin pass-through for DIO1, which will essentially connect the DIO1 on the FX3, so on the master side, to the IMU DIO1. And since there is no IMU DIO1, what this actually allows us to do is use or generate a clock signal or a data ready signal from a master device.
It's cheating, but
yeah, it's cheating, but it's useful for testing.
Yeah.
So if we start this, we're actually now applying a 100 hertz data ready signal to the buffer board, and because this pass-through is enabled, it looks like it's coming from the IMU, essentially.
Yeah, and the pass-through is bidirectional. It's an analog switch. It's not a it's not a, and I don't know, anything else, right? That would be directional. It's not passing through anything. It's literally just connecting the 2 pins together.
Yeah, it's essentially taking the wire, the master DIO1 coming out of this FX3 board and connecting it to the IMU DIO1 directly. And what that actually sort of brings back up a good point. So you were talking about now you can know exactly when this IMU timestamp was taken. What you can also do using this pin pass-through is if you have a PPS signal, you could actually apply the PPS signal to say like DIO2, and then actually configure the IMU to operate in PPS mode. So that way both the buffer board and the IMU could be synchronized to a single, like highly stable clock source.
Yeah, and then you'll have the time reference. You'll have all the good things that you would need.
Yeah, and it should be pretty simple to get that initial synchronization, because all you have to do is program those UTC timestamp registers and then write a single command. Which you can also do over USB if you're really feeling ambitious. But anyway, so right now, if we look in here, we can see the buffer is actually full because we have this 100 hertz data ready signal being applied. And so we can clear it, and then we'll see it fills up real quick. Slower than I would have thought. Well, either way. Let's do like 5. So what I was actually going to show you is how you can actually what you can actually do to measure the sort of the phase delay of the data ready signal using this PPS input. So if we look on the logic analyzer right now, these are actually mislabeled, but we see we've got this 500 hertz, like air quotes, data ready signal that's coming from the IMU, and then we've got this nice 1 hertz PPS signal. And so what we can actually do is if we go into the register logging application on the FX3, gotta add all sorts of registers.
So, and right now, where the data is the buffer is currently completely full. You've captured all the data that that fits in a buffer, and now all you're going to do with this register logging GUI is you're just going to strip the data and the timestamp and everything else from it, right?
Yeah. So right now the buffer is full. It's sitting at whatever 1,280 samples, and so I was just going to dump out all those samples. And what we can actually do, so I want to bring down the stall time because at 100 microseconds it takes a while. So you can actually, when you're just talking to the buffer directly and not going to the IMU, you can set the stall time pretty low. And you can also bump the S clock up a little bit, so you can set it up at 10 megahertz.
It's 5 times more, a little bit.
Yeah, just a hair faster. That is one advantage of this thing, is you can actually communicate much faster with like some of the 16470 parts than you can just directly communicating to it, because the micro has a much higher clock.
Right. And well, and what's nice there is if you know, a lot of people have been concerned about, well, how do I catch up? And you know, if my IMU is the same speed, that this is exactly how you catch up. I mean, you can go really fast.
Yeah, and especially I'm working on doing a burst data implementation where you will actually be able to read the entire buffer output in a single sort of S clock or a SPI period. That's not done quite yet, but I'm pretty confident I get it working. And what that'll actually allow you to do is really like get data out of this thing quickly, because essentially you'll be able to drop chip select and just dump out the entire buffer contents.
Yeah, in a single transaction. So as long as your receiving device can fit, you know, what is it, 16 times or 8 times whatever number of registers in there.
Yeah, but anyways, so what I was going to show with this PPS signal is we can actually go in here, we can start capturing, and then I'm going to actually clear the buffer. So if you write 0 to buffer count, it actually dumps the entire buffer contents. So we're going to clear the buffer and then stop capturing. And so, oh no, hang on. I don't actually know where I cleared the buffer in here because I don't have the logic analyzer probe on it. Oops.
Oh no.
Yeah, hang on. I need to buy another one of these logic analyzers because I have to keep moving it around between different devices. It's kind of annoying.
I can get you another set of cables, actually. I think I have another set that you can.
Yeah, that could be useful to have.
Yeah.
Here we go. Gonna redo that one time. So what I'm trying to do is I'm trying to clear the buffer so that way we actually know where the first PPS edge is during the buffer data acquisition. Now we can make this a little easier. We can go set the buffer length to like 2 bytes, just so we can fit more buffers, so we get a little more time and latency on it. Yeah, there we go. And so if we go back and do that again, we've got this buffer count register, which we can write 0 to clear. So we're going to say we're going to write 0 to this. And so that actually should have just dumped the full buffer contents, and then they were reaccumulated. So if we look in here.
There it is.
Yep, so right here we sent the clear buffer command to the buffer board. And so then we actually accumulated up a whole bunch of buffer data, which we can actually retrieve right now using this register streaming form. So we go in here, soup, just dumped out the whole buffer, 10,000 samples.
Nice and fast.
Yep. And we can actually go look, and we should be able to find, so we've got, essentially, so what's in here right now is we have this UTC timestamp, right? So we have the UTC timestamp lower and UTC timestamp upper. And so we should see at some point the UTC, oh, nice and early, the UTC timestamp actually rolls over, right? So it goes from 22,629 seconds to 22,630 seconds. And at that time, the first IMU sample after the PPS sync edge came in 802 microseconds later. And so if we actually go and look on the logic analyzer, so we know we cleared the buffer here, and then we got a falling edge on the PPS signal, right? And so I have it set to trigger on the falling edge, and then the next IMU rising edge should have came in 800 micro. Yep. Yeah, it's off by a little bit. That's weird. Oh no, 802. That was right on the money actually. Never mind. So it's 802. Oh, 801. 801. So it was off by a microsecond, but.
Yeah, I think that is perfectly fine as far as uncertainty is concerned. So.
Yeah. Well, also this thing's, I mean, the logic. Who knows if the logic the logic analyzer should be pretty accurate, but I'd say a microsecond precision on your timestamping is acceptable. And so what's really cool about that is, so we know that we've got this ultra stable GPS signal that could be coming in, and we can say we know for a fact that this IMU data ready edge occurred 800 microseconds after the GPS edge came in. And so not only is the UTC timestamp really accurate just because your GPS signal is really stable, but you also know within that period how the exact timestamps.
That is perfect, and that's awesome. That's
Yeah,
gonna make
yeah.
a whole lot of people's lives a lot easier.
Yep, and all of that data is actually included within each buffer sort of entry. And then we also have in each buffer entry, there's a buffer signature, which that's just actually a checksum that you can use to validate that the buffer data that you read back is correct.
And that's calculated dynamically based on the size of the buffer, right? So
yeah, that's actually, yep, that's calculated based on the buffer contents. And so if you have the buffer set to say you only want to read one register, right? So you just have these two values. It'll just be the checksum of the buffer timestamps plus these two values.
Nice.
Yeah, so that was.
I'm gonna say, do you want to go over just the basics of like reading and writing like how you read and write data using the buffer?
Yeah. So
Like,
I guess I was just showing you some of the diff from essentially what I had before, but I guess since we're recording this, so the general theory of operation for this thing is it has the exact same SPI interface that like most of the iSensor's IMUs do. So you put a address, or I can show you on this page actually. You put an address in the upper 8 bits of each word, and then if it's a write command, you put the write data in the lower 8 bits of each word. And so what I have right here is I put hex 4 into the upper 8 bits, which that means I'm reading address 4 on the IMU. And so this buffer write data that's in here on page 254, that is actually the exact data that gets transmitted to the IMU over the SPI bus for each buffered data capture. So the general way this thing works is when you're actually performing the buffered data capture, every time the IMU generates a data ready pulse, every time it says that it has new data, this whole sequence of SPI data will actually be transmitted to the IMU, and all of the SPI data, the corresponding SPI data that the IMU responds with, will be placed in these buff data registers. Or actually, well, it's placed into memory, and then when you read buff retrieve, it actually gets dequeued from the queue in memory and placed into these buff data registers. So I can actually plug back in the IMU. I don't know why I unplugged it.
For the I think the data ready pass through, which.
Oh, that's what it was. Oh, I should probably. Uh-oh. I think I unplugged the FX3.
Actually.
Hopefully this Nimitz part is okay getting plugged in a pin off.
Yeah, it'll be fine.
Oh, well, I'll find out. So the USB virtual serial port does not like being unplugged.
Yeah. Oh, whoa.
What is my computer doing?
Oh, there's probably a dialog window somewhere.
I don't know. Let's just kill the whole thing. So yeah, the takeaway here is you shouldn't go and accidentally short your IMU when you're hot swapping it. It's not good for it.
That is bad.
I think it's lined up now. I'll tell you, those connectors are hard to see. I'm just too old, getting old or something. I don't know.
Probably.
But anyways, yeah, let me relaunch this guy. Hopefully, didn't break anything. There we go. And again, the read-write failed just because the stall time defaults to 15 microseconds. Yep. So we were able to talk to the IMU. So that essentially the way this thing is set up is all of the buffer config registers are on pages 253 to 255, which are not used by any of the IMUs. And the way you access those pages is the exact same as the IMU. You just write the page ID to address 0 in the register map. And so if we go in here, like I said, this is sort of the buffer config page, which has all your settings. This is the buffer write data register, which is where you tell it what data to transmit to the IMU during each buffer data capture. And then this is actually the buffer retrieve data page. And so what's really neat, though, is this thing will actually, if you set the page register to a page that's not owned by the buffer board firmware, so not one of these 3 pages, it'll actually pass all of the SPI transactions through to the IMU. So if I set the page to page 0, it'll actually pass through to the IMU. And so I'm actually reading an IMU data count register, status, temperature, all all the actual IMU output registers. And that's because the buffer board knows that we're on page 0, which does not belong to it, so it just passes the transactions through. And so it actually makes it pretty much invisible to any end user application, right? As long as your stall time's high enough, a end user application won't actually know that it's talking through the buffer board to the IMU. And so you can use that to do all your IMU configuration and settings that you need to do. So like if you have to change the decimation or change the GPIO config or whatever you happen to need to do.
Okay. And if,
then,
you probably don't want to use that for data capture, but you know,
yeah, you probably don't. I mean, you could kind of use it for data capture if you wanted to. The issue is there's a decent bit of latency involved. The main use case where I could see someone actually wanting to use it for data capture is if they are using the CLI, because what that could essentially allow them to do is skip having like a separate eval board, right? Because if like normally you need like an FX3 eval board or an SDP or something else to be able to talk to this thing through SPI. But if you use the CLI, you can actually just talk to it directly, and that gets you a very, very, very low footprint eval board solution essentially. So we can go in here and we can read 0 word, or FD is one of the buffer board pages. But if you want to actually read IMU data, you can go and say we want to write 0, 0. So we set the page to 0. And so now the buffer board knows that all the transactions have to be passed through to the IMU. And so then if we go and say read 0F, that's actually IMU data, right? And so if we want to just dump all the IMU output registers, you could say we want to read 4 to, I don't know what it is, but like that. And so you could actually do that a bunch. So you could say read 4, 1600. And that'll actually give you essentially all of the IMU output data. And so that, I mean, there is definitely a use case there where you want to essentially communicate with the IMU and you don't care too much about bandwidth. But I would say you should actually just use the buffer data capture. That'd probably be the smarter way to do it.
Yeah.
So essentially, yeah, and then the way the buffer data capture works is once you're on one of the buffer pages, you can configure the data ready from the IMU and then also some like interrupt signal generation that this thing has. And then, hold up. Oh no, I restarted the FX. I thought I was still running that PWM signal into the IMU, which is not great for the Blackfin. But no, anyways, so then once you've done all the IMU configuration that you want to do, you set up all the control registers and everything and done all the buffer configuration that you want to do, you provide the write data, which is just the list of registers that you want to read. So we could say, I just want to read the data count register a bunch, which isn't particularly useful, but it's nice and deterministic, which is always good.
And something to point out is like so buffer write 0, if you think about it in terms of transactions, you're asking the IMU whenever buffer write 0 comes up for whatever's in register location 4, right? Yep. And then, we still have buffer write 1 because you want to continue requesting the same register, but because SPI is handled in transactions, what you requested in buff write 0 is going to show up when you request buff write 1, because you write data and read data at the same time, right?
Yeah, so yeah, the way the IMUs, I'm sure people know, but the way the IMUs are set up, there's an offset, right? So you send the read request, you say, I want to read at register address 4, and then on the next SPI transaction, the read result actually comes back in. And so if we look in here, we have this buff write 0, and the actual result register from buff write 0 will come back in buff data 1. So if we read this, yep, so we can see there it goes. So we can actually see buff data 1, 53F3, that's the data count register. And so you can see we were getting a bunch of data counts. And then in buff data 0, we were actually getting the old data count. And that's because the buff data 0 is just whatever the last thing the IMU loaded into its output, which in that case was the data count, because that's what I was requesting constantly. And so you can see we're actually not missing any of the data counts. We're just going on through. Well, I guess we missed some. Oh, we missed some because it's full. That's why.
Yeah, because it's full. And you're dequeuing, right? And it's first in, first out. So I guess the reason that read button works is because in this form, whenever you hit the read button, it starts reading all of the registers in this form top to bottom. So it's going to read status, buff count, and then the page ID, status, buff count, and then retrieve. And the retrieve is actually what triggers the ST micro processor to go and pull that from memory and shove it into the outputs, right?
Yeah, that's correct. So if we actually don't go and read buff retrieve, you'll see that these values stay constant. So I'm reading them a bunch by clicking on them, and none of the values are changing. But as soon as we read buff retrieve one time, it'll actually dequeue one buffer entry from the queue structure in memory and place it into the output register. So we can see that we got a whole new sample value.
And you can also configure what happens whenever the buffer's full, right? I think.
Yeah, you can set it to actually keep sampling or discard the newest sample, or rather, you can set it to stop sampling or discard the oldest. So if we set it to 1, it should actually discard the oldest sample when we get new data. Yeah, it's a little bit hard. Well, it's not full yet, but it's a little bit hard to tell what's going on without being able to like plot the data. But essentially, once this thing fills up, it should actually, instead of stopping the sampling process, it should start just throwing away the oldest data. And then you can actually go and configure it back to not do that by changing the buff config back to 0.
Yeah.
And then there's a few other things. This thing has a lot of the same sort of interface that the IMUs do. So we have this user command register, which is for the buffer board firmware, and that actually lets you do some stuff like you can do you can actually clear the buffer. So you see if we look at the buff count, buff count's at 0 because it gets cleared whenever you change the config. But if we go back here and put it on page 255, and also just so people are aware, the trigger for essentially enabling the buffer data capture is going on to page 255. So when you're on page 255, it'll actually read the buffer, or it'll enable the interrupt from the IMU, and it'll start collecting data. And then as soon as you leave page 255, it stops doing that. And so if we look now at the buff count, you can see it's full again, but it should be constant. Even if it wasn't full, it would just be sitting there. And then there's a few different things that are built into the command register, which are all sort of documented in this register map that we have on GitHub. But you can do some pretty neat stuff, like ones that will probably be most useful for people to know about is there's a clear buffer command, so you can actually go and dump the entire buffer contents. And that's
by dump you mean throw away.
Yeah, trash. They just they're gone. And that's mostly useful if you just have a bunch of really old data that you don't care about anymore. So you can actually go and write a 1 to user command. And now if we look, our buff count is now at 0. And then the other ones that are useful is, like I was showing earlier, there's this PPS enable command, and that actually lets you set up the PPS time-based synchronization. And then I think some that actually are really good for quality of life is there's a factory reset command. And what that'll actually do is it'll restore all the buffer board registers to their factory default values. Well, I had most of them at default already, but if you look, like say we can go to these scratch registers and just put some values in there. And you see the scratch registers are at non-default, and we can issue a factory reset, and they're back to their default values. And so that can be kind of useful if you get your thing in like a weird state and you just want to clear it back to the default. And what's worth noting though is when you do this factory reset command, it actually only changes the register values in SRAM. So it changes the volatile register values. So if you set all your configuration registers, right? So like say you go onto the right data page and you're like, I just want to read the data count register a bunch. What you can actually do is you can go into the config page again, and you can actually issue a flash update command, which is hex 8. And what that'll actually do is it'll make it so that all of these register values are now persistent through power cycles because they're saved to non-volatile memory.
Yep. So you configure everything once, and if you're happy with the config and everything else, save it to the SRAM, save it to the flash, and you're done, right?
Yep. So we can actually see if we go in here, and right now this thing's being powered from the FX3. We can turn off the board, and if we turn it off and then check duct connection, it's off. It's not working. And then if we turn it back on, it's working again, and we can actually go in here and look at these registers, and you've still got the exact same register values. So that's really nice. So it's essentially once you get the thing set up, you shouldn't have to set it back up again. yeah, that's the main new features that I had added. There's some additional diagnostics that I have put in. So the status register actually now has a pretty good bit of diagnostics capabilities.
Oh, wow.
Yeah, I put a lot in there, more than most of the IMUs actually. So it has essentially two different interrupt conditions that it can sort of announce. So if the buffer reaches its watermark level, so if it has a given number of samples, it'll actually set this bit. If the buffer gets full, it'll set this bit. If there's a SPI peripheral error, like a hardware error in the SPI, it has a bit for that. It has a bit for if there's a SPI overflow, which that actually is generated when your stall time's violated. And so if we go and actually look here, so the status register is 0. If we go demonstrate that one, if you go and set the stall time to say like 15 microseconds, which is the default, and then try and read from the IMU, we can go back and read the status register, and we have a SPI overrun violation. Ooh.
And overrun just means that you tried to you requested something from the pass-through, from the IMU itself, and before the buffer board could send the data, receive the data, and put it in its output registers, so to mimic the the transaction, you requested data too quickly, right?
Yeah.
Basically.
Well, so the SPI overflow error is actually set when the when the buffer board firmware receives an additional SPI request and it hasn't finished processing the previous SPI request.
Ah, okay.
The overrun one's actually a little bit different. It's set more like what you were saying. It's set when another IMU data ready comes in and the previous capture hasn't finished.
Gotcha.
So if we actually go in here and we can set it back to like 100. Yeah, we can read this guy. So we can go back to and read the IMU page. So if we go to page 3, we can actually set the decimate to 0, right? Which that puts it at a 4 kilohertz data output rate, which with the current configuration, it won't keep up with. And so if we enable capture, it just filled up. But if we look at the status register, we got this bit set bit 4, which corresponds to an overrun. So bit 4 means we have an overrun. That means that we got an IMU data ready, and we weren't finished with the previous capture, so that data ready was ignored, and that means you lost data. So this thing, with the current configuration, couldn't keep up with the 4 kilohertz. And then the 3 over here is bits 0 and bits 1, which means that the buffer watermark interrupt has been generated and the buffer full interrupt has been generated.
And something important to point out as well is, so you're on page 255, which is the page that you would normally sit on to sit there and read data, but the status register that's on that page corresponds to the same status register that's on page 253. It's just that the page exists in more than one location to make it easier for you to just capture the entire thing, right?
Yep. Yeah. The status count and the buff count that are on page 253 are the same exact, or they're always going to be the same value as the one on 255.
Yep. And that's
it's just you don't have to change pages to read the status, because while you are retrieving data, it's very conceivable that you might want to actually read the status and see, like in this case, it's like, oh, I have an overrun error. That means my IMU data production rate is too high. And you wouldn't want to have to go back to page 253 to check that.
Yep, that's just to minimize the overhead, right?
Yeah. Yep. And then we've got a few other things. We have a PPS unlock signal, which had I talked about that earlier?
No, not the unlock. Actually, you skipped DMA error as well. So.
Oh well, DMA error is not actually implemented right now, because I have to finish setting up the IMU burst data acquisition process. But what that essentially is going to be is it's going to be similar to the SPI error. It's when the hardware peripheral in the microprocessor on this thing actually reports some sort of like fault condition or something that went bad. It'll just set this error, or it'll set this error flag. And so the DMA, it will be used for the user SPI burst, which is where you actually can drop chip select and dump out the entire buffer entry, and the IMU SPI burst, where you can actually, same sort of thing but for the IMU, you drop chip select and read out all of the IMU output registers. And then PPS unlock is, again, when you're using that GPS clock and you actually don't get a PPS signal for 1100 milliseconds. And so if we go in here and we actually can enable the PPS signal. So if we go and set this guy to like 4. So you actually have to, again, you have to send a command to enable PPS, and that lets you get really good synchronization on it. So you would send this command to enable PPS, and then we can actually read the status, and we can now see we've got this PPS unlock signal is set, or a PPS unlock bit is set. But if we go in here and we can kind of cheat, we can actually go in and we can say, all right, it's on DIO 3. So if we put continuous reads on, if we just strobe it briefly, you can see it actually clears, and then it resets itself a second later. Because that's saying that it's been over 1100 milliseconds since the last PPS edge. And so that can be useful for a higher level system to be able to easily monitor when they may have lost their GPS signal, right?
Mm-hmm.
And what else have we got? So then we have a few more bits at the end that are persistent. There's a flash error bit, and that's a pretty simple one. That's just set when the persistent register contents. There's a signature that's stored whenever you do a flash update command, and that's set when the stored signature doesn't match the calculated signature. So you can see right here, this is the stored signature, it was CC7F, and then the calculated one was also CC7F, so the bit's not set. And that can actually be used to tell that like somehow your flash memory contents were corrupted, and you should probably issue like a flash update command or check on your system. And then same sort of thing, this one, the flash update error is similar, but that occurs when the flash memory actually reports a fault while a flash update is being performed. And so that's, again, probably indicates some sort of hardware failure. So that's not a good one if that gets set. And then this guy right here, the fault error is generated whenever the processor core generates a fatal exception. And so those are just the Cortex M4 exceptions that can be generated. And those are actually sticky through resets even. So if you get a fault exception, you can actually reset the part and it'll still come back up with that same fault flag. And there's documentation in the, right here actually, there's documentation in here to describe what the various fault codes mean. So if there's a memory error or a bus error or like a hard fault, it'll set different error codes.
Yeah, that's generally speaking. If you see one of those things,
something bad happened.
Yeah, something really bad happened.
Yeah, and then the last one is there's a watchdog timer running on this thing. So if the firmware ever gets locked up for more than 2 seconds continuously, it'll actually reset itself. And that shouldn't happen, but that's what the watchdog's for. It's just sort of weird, erroneous conditions or like a single event upset that locks up your code. And so if the part ever boots up after being reset by the watchdog, it'll set this flag. So yeah, that's essentially the summary of the diagnostics at the moment and the sort of general functionality. These different config registers have quite a bit in them, and that's all sort of documented in this register definition file.
Yeah, and if honestly, if anything else comes up, or if, I'm sure we'll end up with more questions in the future. But I guess as things are found, things come up. Totally open to adjusting things. But
yeah, I mean, definitely at this stage, if there's any features that would be sort of valuable to have, it'd be easier to add them now than add them later.
Mm-hmm. Yeah, I mean, honestly, I think that this is already extremely complete as far as features are concerned, because this solves the problem of time synchronization, asynchronous data capture from the IMU. It solves so many problems.
Yeah, I think the PPS functionality is actually very, very useful, getting that high stability and also microsecond resolution for your timestamps of your data.
Mm-hmm. Yep.